Hello and welcome to ECE 205. My name is Matthew Harris and I'll be your instructor for this course. So briefly a bit about myself. I graduated with a bachelor's and master's in pure mathematics from universities in the US, and I received my PhD in applied mathematics from the University of Waterloo. I have been working as a sessional instructor for about a year and a half now. So yeah, so let's first go through the syllabus and then we'll talk about the first lecture. Okay, so syllabus, kind of standard things, my name, my email if you ever need it. Here's the various TAs and their emails. In theory, you should never need their emails, but they're there just in case. So description from the course catalog. It's pretty vague, kind of not very descriptive. So at the bottom, I'll talk about what we will actually cover when we look over the course outline. Okay, so our website, we will primarily be using Learn as our main website. So you should be familiar with Learn already, but you are expected to check on it every day. So here we have our kind of banner of Marmee the cat and just a few things that I want to kind of point out here. So I added this useful links widget. While we are online, this widget will be updated regularly, like every week, just to help you keep track with the course. So every week we will have a weekly schedule, which I'll talk about briefly. And here you can see where the office hours are and information about tutorials. So let's briefly talk about a sample weekly schedule. So I'm also teaching ECE 108 this term, so I'm just going to use their sample schedule because it's already done. So if you click onto this link for schedule, it'll go to the Learn page for that schedule. And here's the type of things you can find in a schedule. So here we'll have various columns that'll be kind of color-coded for the various days that you have a lecture, and within each one of these columns, we'll talk about the topics that will be covered, the sections in the course notes that those topics cover, and links to see the lecture on YouTube and the lecture slides. So for instance, if we were in ECE 108, you could click that and it would link to the Learn page where that data is. So it's just there to kind of make things a bit more convenient for you. So in addition, we'll have a playlist for all of our online lectures for ECE 205. That link will be here, and information about office hours, tutorials, assignments that are due this week, and assignments that are due in the upcoming weeks will all be located there. So hopefully you find these useful. Hopefully it can kind of help organize yourself a little bit. Like, I do highly suggest sticking with the schedule that's put here in terms of the color coding columns for various days that we actually have classes. Okay, so back to Learn. So tutorials, when we are on campus, these will be actually hosted on campus, but while we are online, these will be hosted on Teams. So if you click this link here, it will do the little pop-up thing and it will pop up through Teams, and this will go to the office hours / tutorials Teams page that you should have access to. If you don't have access to it, let me know. So yeah, so when there's an active meeting going on, you'll be able to join it from here. So there's no active meeting now, kind of obviously, so you can't join one, but that's where you will access tutorials. I do strongly suggest you go to tutorial, so kind of just keep that in mind. Okay, so in addition to this, you have the standard content tab stuff. So here we have our syllabus, which we're looking at now, our course notes for the term. Do note that with the course notes on the first page, there's a hyperlink to download the solutions for the course notes. I do highly suggest you download those and keep that up. Yeah, so if you click there, you can get the solution manual. So that will give you the solutions to the practice problems and any other problems there. In addition to this, we'll have a section for weekly schedules, lecture slides, and the various assignments. And for the assignments, I will upload text files for those of you who like to typeset your work. Okay, so enough of talking about Learn. So next up, textbook. Again, textbook's freely available on Learn. In addition to this textbook, we will be using some handouts later on in the course. Once we get to that point, I'll tell you about the handouts, all that good stuff, but the handouts will be put into this course notes / handout section. Okay, so here's our normal lecture times. So when we are doing things online, I will be uploading asynchronous videos, but when we hopefully transition back to in person on the 24th, Those will be the various times and locations depending on which section you are. In addition to those, here are some extra scheduled lectures that we have. Do note that if you are in section 1, we're not going to have the first makeup lecture, and if you're in section 2, we're not going to have the first makeup lecture, and if you're in section 1, we're not going to have the last makeup lecture. The reason being is if I did that, the 2 sections would be off by exactly 1 class throughout the entire term, and that's just going to be a mess, and we don't actually need that extra lecture to cover everything. So yeah. So next up, getting help. So for this course, we will be extensively using Piazza as one of your primary resources for asking questions, all that good stuff. So here's our Piazza page. You should have access. I enrolled all of you. So if you don't have access, let me know. But on Piazza, you can post any questions you want. I will be monitoring it, and the TAs will also be monitoring Piazza. So for any questions, don't email me, put it on Piazza. In addition to this, we have some office hours. So I have a survey that's currently open. So you can fill this out to fill out the hours that you would like to have office hours. And I'll try to best accommodate whichever ones have the highest number of people that fill them out for that particular time slot. Okay, and during office hours, you can ask questions on any of the lecture content or any of the homework content as well. So if you don't have a particular question on homework, you can just pop in and ask any question on any of the material that's been covered throughout the course. Okay, so tutorials, they will start the week of January 10th. We're going to have weekly tutorials. Here are your tutorial times. These will be synchronous while we are online and offline. Again, if we are online, you will go to that Teams page to see the tutorial, and if we are offline, you will go to the room, okay? So yeah, I strongly recommend you go to tutorials. They will cover sample problems that can help you on the assignments, okay? And there you can ask any questions that you have as well. But the primary focus will be on having a handful of examples to go through. Okay, so the marking scheme for this course. So 30% written, 30% final, or midterm, 40% final. So for written assignments, we're going to have 9 written assignments, and we'll take the best 8 out of 9. Okay, so in addition, we have this clause here. Need to fix that typo. This here should be ECE 205, and that will be updated in the version you get. But you need to get at least 35% out of these 70 percentage points between the midterm and final to pass the course. If you get less than 35 out of the 70, your mark will be x divided by 70, where x is the percentage points that you get between the midterm and the final. Okay, so written assignments, again, there'll be 9 written assignments numbered 0 through 8. Note that for assignments, we'll be using CrowdMark. You should be familiar with CrowdMark, so I won't say anything there. If you have questions, ask on Piazza. And they will be due at 9 p.m. on the dates below, so mostly Wednesdays, with the Tuesday, April 5th being the last day of classes for kind of a smaller assignment. Okay, so for remark request, you need to bring your grading concerns to me within 1 week of receiving the graded assessment. If you do not meet within this limit, then I won't do a remark, so definitely keep an eye on it. And also, before submitting a remark request, make sure you check the common errors that will be uploaded to Learn, just to make sure that your concern isn't one of those common errors. If you do make one of those common errors, don't send me an email for a remark request, but you can ask on Piazza why that was a common error, and then everyone else can see the answers there, that type of thing. Okay, so do not cheat. Do not use the internet to look up full or partial solutions. Don't use things like Chegg, Course Hero, Wolfram Alpha, any online calculators, anything like that. The use of such methods is strictly prohibited, and you will get a Policy 47 violation if I catch you. And I do keep an eye on various websites. I have an internet spider that checks things, so make sure you don't cheat, okay? It's not worth doing. The consequences are pretty rough. Okay, so exams, we have a midterm that's scheduled for February 16th from this time. I'll tell you the room number as the things get closer, and we will have a final that'll be scheduled by the registrar somewhere between these dates. I'll upload the syllabus once I know the final date. Okay, tentatively, these will be are in person, and I'll let you know if things change to where it goes online, but that's up to the university and what happens there. So plan on an in-person exam where it's closed book. So definitely don't kind of get behind in the concepts and the definitions and all that good stuff. Okay, so calculators, you can have a pink tie or blue goggle calculator, as in this calculator regulations page. They are permitted on the midterm and the final, but you will not need a calculator for either. It's just there if you want some basic addition type things. Okay. Missed assignments. If you become ill or you are first to miss an assignment, get a verification of illness form or other official documentation. And if you have proper documentation, then we can make that, well, we can exempt you from that assignment that you missed, that type of thing. So say if you missed one assignment, then you would be exempt from that particular assignment, and your new assignment portion of this total here would then be best 7 out of 8 instead of 8 out of 9, that type of thing. Again, if you miss the final or midterm, you do need to have a VIF for that, and if you miss the midterm, we'll normally just put 70% of the weight on your final. And if you miss the final, then with proper documentation, if you have at least 30 out of the remaining 60 marks, then you could be eligible to get a INC grade. Okay, so COVID plan. So we're starting online, so you'll see how this course will run in an online setting, but my COVID plan for this course is basically if we need to go online for a short period of time, I will replace the in-person lectures with asynchronous online video lectures like you're getting now, like you're currently watching, and then I will be posting my lecture slides on Learn. So you'll have access to all the stuff just like you're having access to it right now. In the event that an individual student needs to self-isolate, then you will be provided with the lecture slides that will still be posted on Learn. And then you're more than welcome to attend office hours to ask any questions, and you can, of course, post any questions that you have on Piazza. So there won't be an online version of the lectures while the class is running in person. Just, it takes a lot of time to make these nice videos like this, so I'm not going to run videos and in person. There's not enough hours in the day for me to do that. Okay, so this is a blurb that the university recommended I add to my syllabus, so I have. Basically, if something really goes bad, then we could change some of this information, like the weighting here, maybe fewer assignments, something like that. I honestly don't expect that to happen because this course setup has been designed to work both in person and online, so there shouldn't be any issues that come up where I would need to access this. So yeah, it's just there just in case. Okay, so then we have our standard things: academic integrity, do not cheat, grievance, discipline, appeals, all good stuff. Note for students with disability. So if you need extra time on exams and have a documentable reason for why you can have that extra time, make sure you contact accessibility services. So mental health, especially when we're dealing with COVID, going on an online type thing, stress, anxiety, depression, all of that is much more, you're much more likely to experience any of that. So if you find yourself having issues with the stress of being online, anything like that, here's some off-campus resources that you can contact, and there's also on-campus resources that you can contact, which are available via this mental health widget here. So make sure you take care of your mental health within this online type setting. Yeah, you all know the kind of spiel there. Then the standard diversity statement here. Okay, so what are we going to learn in this class? Okay, so the class kind of splits up naturally in two halves. First, we talk about solving differential equations and boundary value problems and initial value problems. So that's this first 3 weeks where we talk about kind of the standard ways of classifying differential equations and then how you'd go about solving these various differential equations. We then turn our attention to the harmonic oscillator, which is a classic application of a lot of the material that we'll cover in the first 3 weeks. And these two kind of catch-up slides are there in case one of these topics takes a little bit longer. We can roll over to this catch-up period. And then after that, we'll talk about Laplace transforms and how to use them to solve various differential equations, initial value problems, all that good stuff. Okay, so basically Laplace transform is a very powerful method that you can use to solve a large class of differential equations and various problems. So that will be the weeks 5 and 6, we'll focus on that. After we do that, we kind of change topics quite a bit. We talk about convolution and then tie that into Fourier series. So Fourier series is this remarkable idea that a very large class of functions can be written exactly as an infinite sum. So in practice, Fourier series are used for a lot of things, for instance, transmitting information via Wi-Fi or solving a lot of partial differential equations, that type of thing. So the second half of this course, basically weeks 8 through 10, are all about solving Fourier series, and when we get to this point, most of the material will be given via handouts. So just keep that in mind. Once we get to there, we'll be switching text from the classic text that we're going through to handouts that I will give you when the time comes. Okay, and then finally we end with a discussion of the Fourier integral, which is kind of an infinite dimensional analog of the Fourier series, and that will make a little bit more sense once we get to that point. So yeah, that's the kind of TLDR of the syllabus. If you have any questions, ask away on Piazza. Piazza's best because your other classmates can see your questions as well. Okay, so let's get into the lecture now. Okay, so let's get into the lecture. So why differential equations? Why do we care about them? Well, differential equations are a nice way that you can model many real-world problems. So oftentimes you want to know something that's really complex, say the position of a rocket as a function of time. Well, that can be quite difficult to compute, but on the other hand, it could be really easy to, say, apply F is equal to ma to the rocket, figure out what all the forces are, and then use the fact that acceleration is the second derivative of position to solve for the position of the rocket. That's a common way that we derive differential equations. Okay, so let's look at a few applications and go from there. So assume that some virus has a constant reproductive number R0, that the population of people who could be infected is infinite, and once infected, you are always infected. If this is the case, then a rough model for computing how this virus would spread would simply be given by this differential equation here. So here I is the total number of infected individuals, and all this equation is saying is that the change in the total number of affected individuals over time is simply equal to the reproductive rate times the number of individuals that are infected. Okay, so pretty simple equation. It's not going to be applicable for most cases. One, population's not infinite, and there's quite a few viruses where once you're infected, you're always infected, like herpes simplex, but there's lots of viruses where that is not the case. Okay, so that's one example of a differential equation that you could use to model some real-world problem. Next up, Newton's second law. Well, Newton's second law actually turns out to be a really rich source of deriving differential equations. So we know F is equal to ma. We know that the acceleration is just the second derivative of the position function. So if I know the forces acting on an object, I can plug them in here, and that gives me a differential equation I can solve. Okay, for example, if I apply Newton's second law to a ball in free fall with mass m, then I can get this model here, where P is going to be the position of the ball at any point in time, and F of P is going to be the net force acting on the ball at position P. So let's just give an example. So here, say if I have a ball like this, and I can have some forces that act on it. I might have gravity going down, I might have some force applied by wind pushing me this way, and I could have some drag going up here that tries to slow down the ball. So these could depend on time, so I could change this to f of p comma t, but for this simple model, if I'm just saying that it only depends on p, if I encapsulate all of these forces by taking the sum and plugging the forces into here, I would get a differential equation that I might be able to solve for p. Generally speaking, a lot of differential equations you can't solve analytically, but some you can. So that would give me a differential equation that would model the position of this ball over time if I could solve for p. Well, I mean, it models it either way, but it would be nice if it could solve for p. Okay. So in the first half of this course, we're going to learn how to classify and solve various ODEs, such as these above equations up here, And later we're going to discuss partial differential equations, or PDEs, such as this equation here, which is known as the wave equation. So note here, u depends on two variables, x and t, and here I have a partial derivative here and a partial derivative here, thus partial differential equations. We'll talk about that in a bit more detail later in this lecture. Okay, so again, our focus is going to be on ODEs, and we'll discuss a little bit about PDEs. Not very much, but just dip our toe in the water, so to speak. Okay, so let's talk about classifications of ODEs and PDEs. So based on what type of ODE or PDE I want to solve, I might use a different solution method to try to look for a solution. Okay, so let's look at some ways we can classify these. So first, this is more about the variables of an ODE, but we can talk about independent and dependent variables. Okay, so so the unknown function of a DE, or differential equation, is known as the dependent variable of the DE, and the variables on which it depends are called independent variables. So let's look at a couple examples. So for the equation we examined earlier, here you can see that I will be the dependent variable. Why? Because I is the thing that I'm taking derivatives of, and ultimately it's usually the thing I'm interested in finding what it is. Okay? And from here, the independent variables are just going to be t, because that's the only thing I have kind of sitting in here that I'm taking a derivative of. Okay, so from here, what is this r naught? Well, r naught is known as a parameter. So for a fixed constant value of r naught, I could solve this for I as a function of t. So that's why it's a parameter, because we're treating it as a constant. Okay, so let's look at another example. So for this equation here, the wave equation that we talked about earlier, in this case, what do you think the dependent variable is going to be? Well, it's going to be the thing that I want to solve for, and the thing I want to solve for is u. So u will be the dependent variable. What about the independent variable? Well, it's kind of a trick question. There's two variables here, x and t, that u depends on. So both x and t are going to be independent variables. So generally speaking, if you have more than one independent variable, usually you're trying to solve for a PDE rather than an ODE. Okay, so in addition, I have this mu again. This mu is just going to be a constant, so that would be a parameter. Okay, so next up, let's talk about the order of a differential equation. So the order of an ODE or a PDE is the degree of the highest derivative. So what do I mean by this? Well, if I take a 50th derivative, then it would be a 50th order ODE or PDE, depending on what type of derivatives I take. So for one example, what order do you think this is? Well, the highest derivative I'm taking is the first derivative here, so this would be a first order ODE. Okay, so next, what about the wave equation? Okay, so I just fixed a typo here that I just noticed. This should be an x, not t. On the first slide, it was a t. It's now an x, and it'll be an x in the uploaded versions of the slides. Either way, this will be a second order differential equation because I'm taking the second order derivative here. Okay, so let's look at one final example here. So what would the order of this equation be? Well, if we look at it, recall that this parentheses around the n is saying take the nth derivative. So here we kind of have to know what n is to be able to classify this. For instance, if n is 0, then the highest order derivative would be this one here. And if n is greater than 0, then it will simply be this term here, or if it's 1, it doesn't matter which one you pick. So this will be an nth order if n is greater than 0, and it's going to be first order if n is equal to 0. Okay, so that's how we classify ODEs or PDEs based off their order. Now, I've been kind of loose talking about ODEs versus PDEs, so let's formally define what I mean here. So a differential equation that only contains ordinary derivatives is an ODE. Okay? On the other hand, if it contains at least one partial derivative, it is a PDE. Okay, so let's look at a couple examples. This is going to be well, I'm taking an ordinary derivative here, there's no partial derivatives, so that will be an ODE. On the other hand, this will be a partial differential equation because I'm taking these partial derivatives here. Okay? So hopefully pretty straightforward. Next up, a very important classification of differential equations is linear versus nonlinear. Generally speaking, linear equations are much easier to solve than nonlinear equations, and kind of nonlinearity is where all the interesting stuff, at least in my opinion, happens. That said, my PhD is in fluid mechanics, so I'm really interested in the nonlinear stuff because you get some interesting phenomena there. Okay, so a differential equation that contains no products of terms involving the dependent variable is called linear. Okay, so on the other hand, if it is not linear, then we say it is nonlinear. So to better understand this kind of difference, let's look at a few examples to clarify things up. So if I look at this equation and this differential equation, what's going on here? Well, for this equation, the dependent variable is going to be y, right? And for this equation, the dependent variable is going to be u. Okay, so in the first case, this term here is the only location where y appears, and here I don't have any products of terms involving y, it's just the second derivative. So this will be linear. And on the other hand, here I have this term involves u, and this term involves u, but none of them involve products of u. So both of these will be linear differential equations. This one's a ODE, this one's a PDE. Okay, next let's look at two more examples. So here, in this case, my dependent variable is going to be y, and in this case, my dependent variable is going to be u. Okay, so in this case, I have y times the second derivative of y. Well, that's a product of terms involving the dependent variable, so this will be nonlinear from here. In this next term, I have a u of t. Well, this term is perfectly fine. It doesn't have a product of the dependent variable u, but this extra term over here, this is a problem because it has u times the derivative of u. That's a product of terms involving the dependent variables, so both of these will be nonlinear. So on a side note, this is known as Berger's equation, and it appears in applications such as the dam break problem. To be a little bit explicit there, say if I have a dam and all of this over here is water, and the dam breaks, all of a sudden this hump of water is going to go this way. This is one way that you can model that fluid dynamical phenomena. Okay, so let's introduce the final classification of differential equations that we will talk about in this lecture. We'll get more as we go along, but homogeneous versus inhomogeneous equations. Okay, a differential equation where each term depends on the dependent variable is called homogeneous. Otherwise, we call it inhomogeneous or non-homogeneous, different terms for the same thing. So let's look at a couple examples. So this equation here, I have three non-trivial terms, this one, and this one. And you can clearly see that y is going to be my dependent variable. So my dependent variable is just the y for this case. And here, y appears in each one of these terms, either second derivative, first derivative, or just the thing. So in this case, this will be a homogeneous differential equation. On the other hand, if I examine this thing, y again is going to be my dependent variable, and y appears in these first three terms, but it does not appear here. So this would be an example of a non-homogeneous or inhomogeneous differential equation. And later on, we'll talk about how you want to go about solving these various types of equations, but I just wanted to introduce these classifications here. Okay, so again, there are many other ways to classify differential equations, and we will introduce a lot more of them throughout this course. Okay, so now we say had some physical problem, we set up a differential equation. Well, what do we want to do now? Well, we want to solve the differential equation, right? Like, I'm not setting up the differential equations just for fun. I really want to understand something that's modeled by the differential equation. So a solution to a differential equation is a function that satisfies the differential equation. Okay, so if you take the function, say y, plug it into the differential equation, you get that the differential equation holds. So note, solutions need not be unique nor exist. Okay, so this is kind of different than a lot of things that you may have done in the past, but uniqueness isn't guaranteed, existence isn't guaranteed, and generally speaking, you need to prove uniqueness and or existence. So let's get our hands a little bit dirty and look at one example. Find all solutions to this differential equation for x is greater than 0 and plot several of them. Okay, so let's go over to Mr. Paint and do this problem. So stick with that zoom. So here, what do we want to do to try to solve this differential equation? Well, just notice here, what's my dependent variable? Well, y is my dependent variable. That's the thing I want to solve for. So if I treated this like any other expression you'd want to try to solve for a variable y, a natural first thing to do is try to solve this thing for y prime. Get y prime is equal to something. Well, in this case, since x is greater than 0, I can just divide by x. So I can simply, as my first step, say, hey, y prime is going to be equal to 3x plus 1, all divided by x. Okay, so now I want to solve for y. So natural question is, how can I undo this y prime? Is there something from calculus that I remember that it's not a derivative, but oh, integrals. So what we can do is we can integrate both sides of this equation for this case. So I can integrate both sides with respect to x. On this side, I get this. And on the other side, I'm going to get the integral of, well, this expression here, dx. Okay. So that made some progress. So from the fundamental theorem of calculus, on this side, I'm just going to get y. Notice I would get a plus c, but I'm going to get a plus c on the other side as well. So I'm going to ignore the plus c since I'm going to introduce one on the right-hand side. Formally speaking, you could write this as y plus c, but you don't need to. It's a bit messy. I'm just going to write it as y. Okay, so on the other side, what am I going to do? Well, I need to integrate it. So let's just kind of look at this and say, how can I simplify this expression? Well, should be able to note that I could, hey, just split up this fraction. So I could first write this as the integral of 3, right? X divided by x goes away, plus 1 over x dx. Okay, now from basic calculus, the integral of 3 is 3x. The integral of 1 over x is ln of the absolute value of x, which I'm going to leave the absolute value here, even though for this case I don't need to, since x is strictly greater than 0. And do not forget the plus c. So notice here in this question I say plot several of them. How am I going to go about plotting several of them? Well, I need to have several of these curves. So I need that plus c to plot these. Okay, so now what I'm going to do is I'm just going to jump over to plot this. So you could do this by hand. Here I wouldn't really expect you to do something like this by hand. So let's plot these guys out. So for any fixed value of c, I get a different solution, right? That's kind of nifty. So let's just plot this for different values of c. So if I do 3x plus ln of x plus c, and here c, I'm just going to let that take on some various values. So first, natural number to say is, hey, what if c is 0? If c is 0, then I get from here this nice little plot here. So I could just plot this, and let me just change the zoom, so I'll be back in a second. Okay, so here's one solution. Note, I only want things for x greater than 0, so I'm ignoring everything to the left here. And that's the solution for c is equal to 0, and we can plot this for different values of c, right? Like I could do c is equal to 1. So if I do this, it's just going to shift it vertically, right? So I'm just going to get all these curves where I have different vertical shifts happening. Okay, so in this case, there's infinitely many solutions because I just found infinitely many solutions, better color. It's really this plus c, the constant of integration, that's allowing me to get all of these various solutions. Okay, so through the magic of pausing the video, here's a cleaned up solution of this. Okay, so there's the solution we just did. So note the graph of the solution to the DE is called a solution curve or an integral curve. So integral curve's kind of a older term, but generally speaking, one of the ways that you can try to solve different equations is integration, as you kind of noticed here. So that's just where that nomenclature comes from. Okay, let's look at another example. Find all solutions to the continuous eigenvalue problem, this thing here. So if you recall from linear algebra, we've previously talked about eigenvalue problems. So why would I call this an eigenvalue problem? Let's just use that as our starting point here. Well, an eigenvalue problem was of the form ax is equal to lambda x, right? So if you notice here, if y is kind of acting like x, lambda is lambda, and a is being this differential operator. So just by the similarity between something of this form and this differential equations of this form are often called eigenvalue problems. Okay, so a little bit of nomenclature there. You don't need it for this problem, but I want to start trying to make these connections between linear algebra and differential equations kind of early on, because there are a lot of really deep connections between the two. Okay, so how would I go about trying to solve this? Well, if I rewrite this in a different way, it's just y prime is equal to lambda times y. Okay, so here I have kind of y's on both sides of this equation. So a good thing to do would be to assume y is not equal to 0 and divide by y. So here I'm saying if y is not equal to 0, then I can do this division by y. So throughout this course, be very cautious about dividing by 0. That's probably going to be one of the most common errors made for several bits of this course. But if y is non-zero, which I'll check that later, then I can rewrite this as y prime over y is equal to lambda. Okay, so now here I could just differentiate or integrate this thing with respect to x. So if I do that, the integral here, this would just be dy, because y prime's dy dx, divided by y is simply equal to the integral of lambda dx. So let's clean this up a bit. Okay, and again, here I'm just using the fact that y prime is dy dx and canceling the dx's there. You don't have to do it that way, but it's a valid way of doing it. So on this side, if I integrate this, what would I get? Well, dy over y, that integral is simply going to be ln of y, right? And again, I want the absolute value of y, and I'm assuming y is non-zero, so nothing bad happens here. And this would simply be equal to lambda x plus c. Okay, so from here, I want to solve it for y, right? So how do I isolate this for y? Well, I can just take e of both sides. So e of the ln of absolute value of y, well, just write that thing out, is simply going to be equal to e of the other side. So that will be equal to e raised to this power here. Okay, so let me give myself some more space. Okay, so pretty straightforward simplifications. This thing on the left-hand side, that's simply going to be y, right? E and ln cancel each other out. And on the other side, this I could rewrite as e to the c times e to the lambda x. Okay, and e to the c, I'm just going to give that a name. I'm going to call it c1. So this will be c1 e to the lambda x. Okay, so if y is non-zero, then my solution is going to be this thing here in green. Okay, so again, here I just kind of isolated for y, all the terms that involved y, and then I could just integrate to get the solution. So yeah, it's kind of a nifty little technique that at least worked for these two cases. Okay, so now what about y is equal to 0? So I assumed y was non-zero to get to this point. Well, it turns out that if y is equal to 0, it does satisfy the equation, but it also turns out that if I pick this value of c1 to be 0, then this general solution that I've put here in green contains the y is equal to 0 solution. So you can ultimately say that the solution to this will simply be y is equal to c1 e to the lambda x, where c1 is just some real number. Okay? So it just turns out that in this case, we're lucky that if we ignore the fact that we started with this constant being written as e to the c, which can never be 0, then we can actually get all of the solutions of this from this form. Okay, so that's another example of solving one particular differential equation. And do note, after I'd solved the equation, when I wanted to handle this y is equal to 0 case, I simply plugged it into the equation to verify that it was a solution. In general, that's how you verify that something is a solution to a particular differential equation. Okay, so later on throughout this course, we'll talk a lot more about the details of different solution techniques, but here you've seen two different techniques that basically involved isolating for y prime or stuff involving y prime and integrating. That's a technique that works decently well for first order differential equations. And we'll discuss it more in the next lecture. So let's talk about initial value problems. So sometimes we have some initial data that can be used to find a particular solution to a DE. So if you look at these previous examples, I had the C1 as an arbitrary constant, and I had the C as an arbitrary constant. So there's infinitely many solutions, but what if I know some information about the thing I want to solve? So for instance, say if I know the initial position or velocity of a projectile. Well, it turns out that I can use this extra information to build what's called an initial value problem. So an initial value problem is simply a differential equation along with some initial conditions. It could be one single condition, or it could be multiple conditions. Generally speaking, you'll want the number of initial conditions to be less than or equal to the order of the differential equation, but we'll talk about that later on. Okay, so let's look at an example. Find a solution to this initial value problem. Well, okay, how might I want to go about doing this? I want to find a function y, because y is the thing that's my dependent variable of this differential equation, such that when I take its derivative, I get 1 over x, and such that y of 1 is equal to e. Well, this is already in y prime is equal to something form, so let's just integrate this. So if I integrate both sides, so y prime by dx, and integrate the other side with respect to x, 1 over x dx, well, this is pretty straightforward calculation, right? On this left-hand side, I'm going to simply get y. I'm going to ignore the plus c because I have an arbitrary constant on the right-hand side again. So from here, I just get y, the integral of 1 over x. Well, what's that? Well, that's just ln of the absolute value of x, okay? And I get my arbitrary constant. Okay, so that was pretty straightforward. So now, how do I use this initial data? Well, since y of 1 is equal to e, why don't I just plug that in? So using my initial condition, I would get that y of 1 is equal to e implies that e is equal to ln of the absolute value of 1, or just 1, plus c, okay? ln of 1, that thing is just 0. So from here, this tells me that c is equal to e. So that's pretty straightforward. Since c is equal to e, just plug that in, and the solution to the initial value problem will simply be y is equal to ln of the absolute value of x plus e. Okay, that's pretty straightforward, and let's circle that in green. Okay, so let's notice something. This ODE isn't defined when x is equal to 0, neither was this y is equal to ln of x thing, right? So this solution isn't a solution for all values of x, but it has some limitations on what x can be. This is a very important idea, and it has a name. It's called the interval of validity. So the interval of validity of a solution y is the largest open interval that contains the initial value of the independent variable or variables on which y is a solution. So note here, x is the independent variable. The initial value for this case was just 1. So the interval of validity for this solution y that we found here is going to be an interval of the form a comma b that's going to contain 1. So 1's going to be an element of this. And it's going to be the largest interval such that this function y that I found satisfies the differential equation. So just kind of eyeballing it from here, I know the differential equation isn't well defined at 0, and that's really the only bad point for the differential equation. So from here, the interval of validity will simply be 0 to infinity. Okay, so later on, we will talk a little bit about intervals of validity. And there's a lot of theorems involving solutions to differential equations where you find a solution on a certain interval, right? Because you might not be able to find a global solution for ODEs, but for this case, as an example, we could find a local solution on some subset of all of the real numbers. So an important thing to note here, sometimes the interval of validity has a physical meaning. So for instance, say if you're solving Einstein's field equations around a black hole, once you actually hit the black hole, there's a singularity where your differential equations break down. So your solution is only technically valid outside of the event horizon. So that would be a physical example of where the interval of validity has a meaning that your physical model that you're using breaks down within those locations, and you need a better model to understand what's happening there. Okay, let's change topics. For an ODE of this form, so a first order ODE where the right-hand side is just some arbitrary function of x and y, and the left-hand side is a function, well, it's just y prime. A direction field is a plot showing the slope f of x comma y at any point x comma y. So why might we want to know what a direction field is, or like, why is this useful? Well, direction fields, generally speaking, are useful for seeing what happens at any point x comma y. If I know what f of xy is at that point, then I know how y is changing at that point, and I can go, hey, like, at this point, this is the direction of the tangent line. Further, these can be used to numerically solve some ODEs of this form. If you have certain singularities here, that method will break down. That's mentioned in the text, so you definitely should check out the text on this for comments there. Okay, so in practice, I can't plot f of x comma y for all points x comma y. So what I do is I plot the slopes on a kind of finite dimensional version. So what do I mean by that? Well, I simply pick a rectangular grid. So here I have my A, B, C, D. That's where I want to plot the stuff. This figure was taken directly from the text, by the way. So here I pick a bunch of points where I want to compute what this slope is. And for each one of these points, I will draw a little vector with an arrow. And the arrow will show the direction that I'm traveling. So let's look at a few examples taken from the text. So for this function here, so for y prime is equal to this function here, this would be an example of a direction field on this rectangular region here. So notice I have these kind of blue curves that are plotted. Let's just zoom into one of these. The natural question is, what are these blue curves doing? Well, hey, if I start in this spot here, I have to kind of travel in the direction of the arrow, so that'll put me over here. And I have to travel in that direction of that arrow, and if I keep chasing this out, just following the directions of all these little arrows, I trace out a curve. That curve that I just drew here, this is going to be a solution to the differential equation y prime is equal to this thing here, right? So by simply kind of following those curves, we can numerically solve some differential equations, or ones of this form, where the thing over here is sufficiently nice. We're not doing much with numerics. I really won't get into the details of sufficiently nice, but definitely check out the book's comments on that. Okay, so here's just another example for this. At every point, I draw an arrow with the slope being given by this function here. So before we go on, one more thing to notice. Notice that these arrows are actually showing the slope of the tangent line to any of these given solution curves at any given point x comma y. That comes directly from the definition of these direction fields, right? So if I have a solution and it satisfies the differential equation y prime is equal to something, then if I take the derivative of the solution, the slope of its tangent line is simply going to be this thing here for any given point x comma y. Okay, so let's look at one example of actually constructing one of these. So draw a direction field for this differential equation y prime is equal to x squared y on the rectangle 0, 1 cross 0, 1. So let's go to Mr. Paint and check this out. Okay, so the first thing I really should probably do is draw this rectangle. So let's just put our xy axes, And then with these XY axes, I'll put little notches on the rectangle that I'm interested in working on. Okay, so let's just say that this thinner line here is going to be my up to 1, and we'll call this line here my 1. Okay, so here I didn't specify how many intervals to show, so let's just do, say, 2. So I'll do something here at 1/3, here at 2/3, here at 1/3, and here at 2/3. Okay, so the grid that I'm going to be using for this example will simply be this grid consisting of these 4 points here on the interior, along with these points here on the edges. So I'll draw all those points in and then be back. Okay, so to know the slopes that I need to draw for each one of these, what do? Well, all I need to do is compute f. So in particular for this case, my f function will just be the right-hand side of this differential equation. So f of x comma y is simply going to be x squared y. But I simply need to compute this function at the various xy points that I drew here. Okay, so if x is 0 and y is 0, I simply get 0. So here I'll just have a point, and I'll do this in blue. So my slope will be 0. So a line with slope of 0 would look something like this arrow here. Okay, and I'm going to use these little arrows to draw them. Okay, so next, if y is 0, so if I'm along here, I will still have a slope of 0. So these arrows will all just look like this along here. Okay, now next up, along here, if x is 0, I still get 0, so I'll have these arrows going this way to represent a slope of 0. Okay, so next up, if x is 1/3, I'll get a 1/9 for the x squared bit. And as I go up here, as y increases, the slope will increase. So I'll get something that looks like maybe some kind of slight slope here, that. And as I go up, the slope will increase. So I'll get a higher slope here. So again, this isn't drawn to scale because at the top, this would be a slope of 1/9. So yeah. And then next, as x increases, so I have a slightly higher slope here, and then like a slightly higher slope here. And then as I go vertically here, it'll also increase. So again, none of this is to scale. I won't ask you to draw a detailed thing here, but that's how to plot these. So just stealing from Wolfram Alpha, a better version of the quiver plot would be this thing here. Better thing replacing my kind of hand-drawn sketched, kind of quite honestly bad version, but it's kind of hard to draw the slopes, with the more professional version here. So generally speaking, this is something you would only do really on a computer. Drawing direction fields by hand is just tedious for the sake of being tedious, so I won't make you actually draw these out by hand. But if you ever had to, that's how to do it. Okay, so with that basically brings our lecture to a close. So for your assigned reading and practice problems, I want you to read sections 1.1 to 1.3, and for practice, look at questions, that should be an S, 1 through 8 on pages 14 through 15. So the text does cover some things that I didn't talk about in much detail here. It goes through quite a few more examples of solving things. So definitely check those out. And next lecture, we'll continue on with section 2.1, where we'll start talking about solving separable equations, which is a class of differential equations that we will introduce next week. So we'll end with the meme. People, maths teaches us that every problem has a solution. Me, the existence of solutions for the Navier-Stokes equations, a partial differential equation, is part of one of the Millennium Prize problems. So if you can manage to do this, you get $1 million to prove that there's a solution. It's notoriously hard. But Navier-Stokes is a partial differential equation that models pretty much all fluid flow. It's pretty general. And in practice, when working on academically working on fluids, you usually make some simplifying assumptions so that you can guarantee that there's solutions within certain constraints type thing. Okay, so I hope you enjoyed the lecture, and I will see you in the next lecture to talk about section 2.1.